Alright, welcome everyone to another exciting episode of the HL Chem Flipped Classroom. I hope you're excited. I'm excited. Carlton's excited. And today we're going to be talking about acids and bases, and specifically pH, how to calculate pH and things related to pH. So there should be a note set posted to the class website that you can follow along with and take notes from, and we'll get ready to go. Okay, so here we are, the pH scale. So we're going to talk about a couple things. We're going to talk about something called the ion product constant for water, and we're going to define pH and make some pH calculations. So, ion product constant for water. Pure water ionizes to a small extent. So just plain old everyday water, some amount of it will be breaking down into hydrogen ions and hydroxide ions. And if we took this thing and we wrote an equilibrium expression for it, we would write this, because the water's not included, and because it's a pure liquid. So this is called Kw. It's just a special equilibrium constant because water is so darn special, and we give it a special name. We call it Kw instead of Keq, and its value is 1.0 times 10 to the negative 14th. So hopefully you recognize that that means that this disassociation occurs only to a very, very small extent. That's a very small Keq. That's a very small value for the equilibrium constant. This is only true at 25 degrees Celsius, just like any other equilibrium constant. It's only going to be true at a certain temperature. And it in fact increases with temperature, and hopefully you can make sense of that in light of delta H is positive, and this is an endothermic process. So if you're thinking back to some of the things that we talked about in the equilibrium unit, hopefully you can kind of fit that all together. This is just another slide that shows kind of the water ionizing, two water molecules smashing into each other, kind of reminding us that in actuality, instead of H+, we're dealing with H3O, the hydronium ion. H+ and H3O can be used interchangeably. It's a little more reality to say H3O+. But anyway, again, we don't include the water in the equilibrium expression, so it looks a little something like that. Now, solutions will contain some concentration of H+ and OH, always. In brackets, that's the molar concentration. When H+ is equal to OH minus, the solution is considered to be neutral. So that's what neutral means, is when those two concentrations are equal to each other. So I made some little writings here earlier. If this is my H+ concentration and this is my OH concentration, if these two things are going to be equal, i.e. the solution is going to be neutral, the only way that can happen is if both these values are 1 times 10 to the negative 7, because 1 times 10 times the negative 7 multiplied by 1 times 10 to the negative 7 equals 1 times 10 to the negative 14. These two things are in fact inversely related. If one of them goes up, the other has to go down, because this value is a constant. It's locked in. So if there's ever hydrogen ions in greater proportion than hydroxide ions, the solution is considered to be acidic. In other words, the concentration is going to be greater than 1 times 10 to the negative 7. If the concentration of the hydrogen ions is less than 1 times 10 to the negative 7, then the solution is considered to be basic. And again, all this is only true at 25 degrees Celsius, but that's just kind of a common assumption we're going to make throughout most of our pH calculations. And yeah, those are inversely related, as I just said. One goes up, the other goes down. Something that's going to come into play later, but I just want to remind you of what happens when things dissolve, when things ionize in water. Acids, unlike most covalently bonded substances, do ionize in water, particularly strong acids like we've talked about. So if HCl dissolves in water, there's my little HCl molecule, which is a gas in its pure state. But if we dissolve it in water, it will break apart, it will ionize, and it will make a little H3O+, or an H+. But the bottom line is, if there's 1 mole of HCl, you're going to get exactly 1 mole of H+. So whatever the concentration of HCl is, it is also going to be equal to the concentration of hydrogen ions in solution. So that's why acids create low pHs, as we'll talk about. They increase the hydrogen ion concentration. It's kind of what they're doing. So pH is the negative logarithm of the concentration of H3O+ or H+ in solution. Now, I know when we hear the word logarithm, some of us freak out a little bit. Some of us might look a little bit like this guy when we hear logarithm. We just want no part of it. Or even some of us might look a little bit like this guy. You know, we're a little scared of him. Maybe we've had a bad experience with it in math class. But really, we don't have to do anything too bad with logarithms. If you know how to use the log button on your calculator, you should be okay. So anyway, back to the story at hand here. I say pH is not what you think it is because you probably have heard of it at some point, but I think people get the wrong idea about it and are often sort of misled by pH. So let's try to figure out exactly what it really is. But first, before we do anything else, I want to get this out of the way. There's a number of critical equations that we're going to be using today and in future days and future lessons. You should have these somewhere handy. There's a bunch of equations here. Unfortunately, you get none of them on the actual IB exam itself. But they're all important, particularly at HL, not so much at SL. But jot these down somewhere and have them for your reference. And you don't get any of them, but we're going to use them so much, and they're all sort of very interconnected, so it's really not that bad. So really quickly, though, what I thought I'd do is do a brief review of logarithms, make sure we understand what they are. We're going to be using base 10 logarithms, but for example, the log of 100, what we're saying to ourselves is 10 to what power equals 100? And it is 10 to the second power, so the log of 100 is 2. What we'll be doing much more commonly, though, is logs of small numbers. For instance, the log of 0.1. 10 to the 0.1 power, or rather 10 to the negative 1 power is 0.1. So the log of 0.1 is negative 1. So pH. Again, we're kind of familiar with the pH scale. We probably remember this either vaguely or completely, that pH 7 is considered to be neutral, and pH 7 down to 0 is increasingly acidic, while pH 7 up to 14 is increasingly alkalinic. It's increasing alkalinity. It's more alkaline, it's more basic. IB often throws the term alkaline around there. So as we go from 7 down to 0, the acidity, really the hydrogen ion concentration is increasing. pH is really just a way to express hydrogen ion concentration. So the hydrogen ion concentration is increasing as we move from 7 to 0. Now, in your mind, you might, if you think about pH at all, you might think about it going from 1 to 14. That's not necessarily true. It might be true that it can go above 14 or below 1. And it also does not have to be a whole number. We can be anywhere in between on pH. So just a quick example here. Again, the definition of pH, literally this math equation here. If you're ever asked to define pH, you should say it is the negative logarithm of the hydrogen ion concentration. That's exactly what it is. And so if we're in a solution where the hydrogen ion concentration is 1 times 10 to the negative 7th, that would be a molarity. What is the pH? Well, we take the negative logarithm of the hydrogen ion concentration. So think this through now. The log of 10 to the minus 7, we're asking ourselves 10 to what power is 10 to the minus 7? Well, of course, that would be the minus 7 power. But then this negative sign here flips that, so the pH is 7 when the hydrogen ion concentration is 10 to the negative 7. And again, it all ties into this equation here and what I was talking about earlier. Neutral solutions, these two values are going to be equal to each other, and they're going to equal 1 times 10 to the negative 7. So when a solution is neutral, the hydrogen ion concentration is 10 to the negative 7, and that corresponds to a pH of 7. What if our hydrogen ion concentration is 0.001? Again, that would be a molarity. What is the pH? All we need to do is take the negative log of that number, the negative log of 0.001. Now these even powers of 10, we can hopefully even do in our head. This would be 10 to the negative 1, 2, 3. This number is the same as 10 to the negative 3. So therefore the log of that number is negative 3, and the pH would be 3. You know, and don't let it freak you out too much if you don't see this. You do have that log button on your calculator. However, you'd have to keep in mind in paper 1, without a calculator, you might have to do some simple logs like this. Now, something you may not ever have heard of is the POH. POH is the negative log of the hydroxide ion concentration. So instead of H pluses, we're talking about OH minuses. And it is backwards, or it is opposite, in the sense that 1 through just below 7 is alkaline, is basic, and 7 through 14 on the pOH scale is acidic. So it runs the other way. And it's less commonly used, but both of them work very similarly, pH and pOH do. So, if you might guess, the definition of pOH is the negative log of the hydroxide ion concentration. So, for example, if the hydroxide ion concentration is 0.00001, that would be 10 to the minus 1, 2, 3, 4, 5. What's the pH? We just need to take the negative log of that number. The log of this number is negative 5, therefore the pOH is 5. So again, here's our ion product constant expression for water, just a specially named equilibrium expression. There's the values put in. That number is 1 times 10 to the negative 14 at 25 degrees Celsius. So when everything's neutral, this is the situation that we're going to be in. Now we can take the log, or rather the negative log, of all three of these numbers, and we get 14 equals 7 plus 7. So what I'm telling you is that this gives us another little equation that's pretty handy. In any solution, the pH plus the pOH is going to equal 14. So that's another one of our handy-dandy equations that I showed you earlier. So this allows us to convert from pH to pOH pretty easily. If the pH is 10, and they must sum to 14, therefore the pOH is, say it with me, ladies and gentlemen, 4? Did you really say it out loud? I don't know. You might make your family think you're weird, but it's good to get enthusiastic like that, I always say. So here's just a bit of practice, and I'd urge you to pause the video for a second and see if you can figure out these problems, and we will come back in a second. Okay, I'm back. How'd it go? Let's take a look. If our hydrogen ion concentration is that, what is the pH? We just need to take the negative log of that number. That number is 10 to the negative 6, therefore the pH is 6. If the hydroxide ion concentration is that number, now here's one that we're not going to be able to do in our head. We're definitely going to need a scientific calculator to take the logarithm of this number, figure out the pOH, but when we take the negative log of that number, it's 2.24. By the way, I'm doing some incorrect stuff with significant figures right here. I'm going to explain the significant figure thing a little bit later in the video, but FYI, this actually does not have the correct number of sig figs. pOH is 2, pH is what? Well, they have to add to 14, so pH is 12. And then if the hydroxide ion concentration is 0.01, what is the pH? Now, we have to do this potentially in a couple steps. There'd be a couple ways to do this problem, but what we should do, I think the easiest thing is to find the pOH first, take the negative log of this number here, which is 2, and then the pOH, well, the pOH is 2, it's negative 2, but the pOH is 2, and then they have to sum to 14, so the pH is 12. The pOH is 2, and the pH is 12. Then there was one more here. The hydrogen ion concentration is 0.00656, and the pOH is question mark. So again, here we should find the pH first, because we don't have any direct information about the hydroxide ion concentration. So we find the pH first, and then we can subtract from 14 to find the pOH. So the pOH is 11.2, or 11.82. Okay, so here's another problem. What if we need to go from pH back to hydrogen ion concentration? Well, we just need to reverse the process, and we're going to use antilogs. So that's another one of the handy equations from the handy equation list. We're going to make the number negative, and we're going to take the antilog. It's basically 10 to the negative 3.45 power. That's exactly what it is. So again, we reverse the process. Instead of doing the logarithm and making it negative, we make it negative, and then we do the antilog. So 10 to the negative 3.45 power, which turns out to be 3.5 times 10 to the 4th. And I'm really bad with my units here on this PowerPoint, but that would be molarity, or mole per cubic decimeter. by what factor, this is a question to ponder, by what factor does the hydrogen ion by what factor does the hydrogen ion concentration change when comparing a pH 3 solution to a pH 5 solution? So I'll let that sink in for a second, but I'll break down and give you a multiple choice here. So comparing the pH 3 solution to the pH 5 solution, is the pH 5 solution, is the hydrogen ion concentration in the pH 5 solution 2 times greater than pH 3, 2 times less than pH 3, 20 times less than pH 3, or 100 times less than pH 3? So why don't you ponder this for a few seconds. I might hum the Jeopardy theme. No, that's probably not a good idea for me to do that, but have you thought about it a little bit? Did you arrive at the fact that it is 100 times less? If you did, congratulations and give yourself a gold star for the day. If you didn't, I've scrawled some things on the screen here earlier that you can probably barely see. Remember that in the pH 3 solution, the concentration of hydrogen ions would be 10 to the negative 3. And in the pH 5 solution, the hydrogen ion concentration would be 10 to the negative 5. So there's 100 times difference between these two numbers. pH 5 is 100 times less than pH 3. And in fact, since pH is a log scale, every notch we go up or down the pH ladder represents a 10 times change. So if you go up 2 steps, that's 100 times change. If you go up 3 steps, it's 1,000 times change. If you go up 4 steps, I'll leave that up to you to decide exactly what that would be. But 4 steps is a lot. So now let's talk about pHs of strong acids and strong bases. Strong acids and bases completely ionize in water, as we've talked about in class. In a monoprotic, 1 proton, 1 hydrogen, strong acid, the concentration of the acid equals the concentration of H+. Goes back to that slide I showed earlier. So what is the pH of a 1 molar HCl solution? Well, again, when HCl ionizes in water, it's going to break apart into a hydrogen ion and a chloride ion, and the concentration of HCl is always going to be the same as the concentration of the hydrogen ions. So if we simply take the negative log of that number, the negative log of 0.1, we see that the pH of a 1 molar HCl solution is in fact 1. Now, a quick note on significant figures with pH numbers. pH are log numbers. They're actually powers of 10 in a way. So it's a little strange, but the significant figures are actually only the digits past the decimal. So this number, the way I wrote it, actually has 3 significant figures, as does this number. So I'm following normal significant figure rules of having the same number of significant figures as the least. So in this case, 3 sig figs here, 3 digits past the decimal in my pH. Now similarly, in most strong bases, the concentration of the base is going to be equal to the concentration of hydroxide ions. So what is the pH of a 1 molar, or 0.1 molar rather, NaOH solution? So this one is going to be a little bit of a different approach because what we're dealing with here is NaOH. So in solution, it's going to dissolve into sodium ions and it's going to dissolve into hydroxide ions, right? And so we know the concentration of hydroxide, so finding the pH immediately is not going to be something we're going to want to do. We're going to find it in 2 steps. The NaOH is generating hydroxide, so let's find the POH, because that's going to be really easy. We're just going to take the negative log of that number, because that is the concentration of both NaOH and hydroxide ions. So we take the negative log of 0.1, we get 1 for the POH, but the question asked us for the pH, so we're going to subtract from 1, and we're going to get 13. My sig figs are not good there. I should have actually 13.000. 3 sig figs here, 3 sig figs here. So if any of that doesn't make sense to you, especially this last part about why we found the POH first, maybe back it up, watch it again. But the bottom line is we just don't know about the hydrogen ion concentration from this number. We only know about the hydroxide ion concentration. So here's a few more examples, and you should see if you could get these, jot them down real quick, pause the video, and we'll come back in a second. Okay, so here we have the answers to the ones we were just looking at. We need to find the pH under all these circumstances. Here we can just take the negative log of that number. 2 sig figs here, 2 sig figs here, because only digits past the decimal are significant. If my HCl concentration is this, the concentration of HCl is the same as H+, so I just need to take the negative log of that number. In the case of giving the hydroxide ion concentration, if I want to find the POH, I want to find the POH first by taking the negative log of that number. That's the POH. Subtract from 14 and get my pH. And then if my NaOH, that's a strong base, that concentration is 0.25. I don't directly know the hydrogen ion concentration, but I do know the hydroxide concentration. So I take the negative log of that number, get a POH, and then to get my pH, I subtract from 14. One more, an HCl solution has a pH of 3.75. What is the concentration of the HCl? So here, we know we can take the anti-log to go from a pH to a hydrogen ion concentration. So I'm going to go 10 to the negative 3.75, and that's going to be my hydrogen ion concentration. But since HCl is a strong acid, those two concentrations are going to be equal. So my hydrogen ion concentration and my HCl concentration in a solution with pH 3.75 is this, 1.8 times 10 to the negative 4th mole per cubic decimeter. Okay, one more here. Hopefully your brain's not completely fried yet at this point. But it says, suppose you add 1 gram of NaOH to a beaker containing 500 milliliters of water. What is the pH of this solution? So the thing that makes this different is it does not give us a concentration to start. We have to calculate that concentration. But hopefully we are all experts at calculating concentration by now. We know that the molarity of NaOH is the molarity of OH. What we're going to shoot for here is finding the POH first. I'm going to turn NaOH, grams of NaOH, into moles just in the normal fashion. The molar mass of NaOH is really close to 40. So 1 gram of NaOH is 0.025 moles. And then I'm going to use my molarity equation. That 500 milliliters from the previous slide, I'm going to change that to liters, and just like we have done many times before, moles divided by liters, that's my molarity, 0.05. So that's my concentration of both NaOH and OH. So to find my POH, I'm going to take the negative log of the hydroxide ion concentration, which is that, and I get 1.3. And then to get my pH, I'm going to subtract from those from 14 and get 12.7. And again, it's just a matter of I don't know the H+ concentration, so I only know the OH concentration. So it's easier to find the POH first before the pH. And that is it. I think we're done for now, ladies and gentlemen. We'll continue to practice this more in class, and we will see you soon. Thank you and good night.